Okay, for the next talk, I'm going to have Mayur up talk to us about BGP EVPN, and then as a reminder, we didn't have it in the guidebook until earlier this afternoon, but right after this we also have 3 lightning talks, so make sure to please stick around for that.
Hello everybody, good evening. I'm Mayur Shetty with Cisco Systems. Today's talk will be basically getting familiar with BGP EVPN in the data center as well as layer 3 data center interconnect. So to get started, okay, what will we cover today will be basically EVPN and the advantages and disadvantages of using VXLAN in a data center, as well as what problems BGP EVPN solves for VXLAN in a data center. And we'll get in a bit of depth with overview of BGP2 route types, which is type 2 and type 5, which is specifically needed in the data center. Also, going forward, we'll go over layer 3 data center interconnect. So basically the L3 handoff feature between BGP EVPN in a data center to MPLS in the WAN side. To begin with, what is EVPN? Ethernet VPNs started off as a next-gen layer 2 VPN solution for the service provider core or MPLS core. So it was basically conceived to address some of the limitations with VPLS. So the advantages EVPN had was basically it would get active-active per flow load balancing, which is very important because VPLS does not support active-active per flow, which is restricted to active standby. Also, EVPN control plane, we can carry MAC routes as routable addresses, as well as it's a multi-protocol BGP. These are the few reasons why EVPN was conceived in the L2 VPN MPLS domain. Now, taking to the same BGP EVPN into the data center, so we have to first understand what next-gen data center needs or requirements are. So some of the requirements are multi-tenancy, integrated routing and bridging, support of various encapsulations, so either VXLAN, NVGRE, MPLS over GRE, or all the flavors in a data center. And more importantly, support and exchange of IP addresses and IP prefixes. So to provide the L3 connectivity from one data center to another. The current status of EVPN is, there's a standardization effort going on in an IETF L2 VPN work group. There's multi-vendor and network operator support who are co-authors as piece of the EVPN MPLS RFC as well as the EVPN VXLAN drafts. So BGP MPLS based EVPN is RFC 7432 and the extensions for EVPN into the data center is currently in the draft stages. Okay, what problems does VXLAN solve? VXLAN basically provides an L2 extension over an L3 underlay using MAC and IP or UDP encapsulation. So what this gets in a data center is basically it helps to move any workload from one L3 boundary to another L3 boundary. Same is the case with VM mobility. And also we get secure multi-tenancy. With secure multi-tenancy, we can basically have traffic and address isolation. And more importantly, the well-known feature is the limitations of VLAN with 4K segments, whereas with VXLAN, due to the VNI field, we can get close to 16 million segments. These are some of the reasons why VXLAN is picked up as the next-gen data center. Now coming down to the challenges with VXLAN. So the base VXLAN technology uses flood and learn with a multicast on the underlay. So with this, so any remote ARP, a remote host or remote VTEPs are learned using ARP flooding as well as anycast unicast flooding. So basically this leads to bandwidth utilization problems, inefficient bandwidth, and also large MAC tables. Whereas if you have a control plane like BGP EVPN in place of flood and learn, so basically the ARPs and anycast unicast traffic is basically dropped at the VTEPs, which is the VXLAN tunnel endpoints, and we don't send it into the L3 underlay. So we'll have a much more efficient bandwidth utilization. And another important factor is centralized gateway. So in the basic VXLAN flood and learn, the VTEPs or VXLAN tunnel endpoints act as L2 gateways. And whereas the default gateway is basically centralized in a core or an aggregation layer, or it must be a spine. So it is multiple hops away from the host. So this leads to suboptimal traffic flows as well as traffic hairpinning in the case of VM mobility. Whereas once we add BGP EVPN as a control plane, so basically the VTEPs act as distributed gateways, and being much closer to the host, we have more optimal traffic flows. Also, we take care of the VM mobility case as well, which we'll discuss further in the further slides as to how that case is taken care. So what is the main barrier? Scaling out large-scale data centers and cloud deployment with VXLAN flood and learn is not feasible. So you need a control plane. Okay, to add to the benefits, which we already listed out earlier with BGP EVPN in the control plane, one more advantage is getting multicast under a free underlay. So most of the data centers and enterprises are a bit concerned about using multicast in the underlays. So with BGP control plane, this problem is alleviated. Another big advantage is active-active multi-homing with per flow load balancing, which is already existing on the MPLS, EVPN MPLS. So we bring it down to the data center. And another big advantage is multi-protocol BGP. With multi-protocol BGP, it adds all the BGP featurettes and knobs, which is already existing. Cases like BGP add path, MD5, as well as the most important feature, the BGP RT constraint. So with an RT constraint, we can reduce the number of route scale on the leaves, with enabling the feature in conjunction with BGP EVPN. Let's look at some of the EVPN and VXLAN terminologies. So a layer 2 VNI. A VNI is basically a VXLAN network identifier, which basically is equivalent to, is mapped to a VLAN. You can basically call it as a VLAN ID, but because it's a newer technology, so we have a much more fancier name called as VNI. And with layer 2 VNI, the moment any VXLAN packet consists of this VNI, so it basically means that it has to be bridge traffic. Whereas for layer 3 VNI, which is basically tied down to a tenant VRF. So the moment any VXLAN packet consists of an L3 VNI, so it means it has a routed traffic. So Anycast gateway. So this has all L3 VTEPs are configured across the same MAC and same subnets. VRF overlay VLAN. So each tenant VRF will have a VLAN, and that VLAN will be basically given a L3 VNI. The VXLAN L2 gateway, so basically this 5 and 1 layer 2 VNI are both tied to each other. So any VTEP or the leaf or spine which supports L2 gateway has the capability to switch bridge traffic. So basically it's between VLAN to VXLAN and back to VLAN. And as VXLAN L3 gateway, so any leaf or spine which or TOR which supports this functionality basically is capable of routing traffic, and this capability is across VRFs, across VNIs. It's not restricted to the same VNI. Here, a brief example of a EVPN control plane. Here we are taking an example of a two-tiered data center having spines and leaves. So the control plane, we have IBGP adjacencies between the leaves, whereas to reduce the scale, we can use a route reflector. And the advantages what we have is basically the host MAC, the host IP, the subnets, as well as the external NLRI information is all carried by BGP. And also the multicast group information is also carried by BGP. And the well-known factor, which is multi-protocol BGP, has the capability to carry thousands of routes, so which will come handy in this case with much more reduced convergence time. Okay, going over the BGP EVPN route types. So the first 4 route types were already part of the original RFC, which is EVPN MPLS. They were primarily used for EVPN as well as PBB EVPN in an MPLS core. Whereas for EVPN in the data centers, we are primarily looking at 3 route types. One is type 2, type 3, and type 5. So we'll go in details on type 2 and type 5, but for type 3, it's an inclusive multicast route. It's basically used for to find the VXLAN tunnel endpoints, and which is used for the egress replication. That is to get the multicast free underlay. So let's look at the type 2 route. Basically being a multi-protocol BGP, it will need a route distinguisher. and it will have a MAC address. The MAC address is basically pointing to the host MAC, and an IP address, which is the host IP. This can be either an IPv4 host or an IPv6 host, /32 or /128. So both the hosts are supported. And there are two labels, label 1 and label 2. In terms of a data center, so it equates to layer 2 VNI or a layer 3 VNI. So if it is layer 2 VNI, it is attached to a host MAC, and you know it's meant for bridge traffic, whereas if it's a layer 3 VNI, it is attached to a VRF, it's tied down to the host. So basically routed traffic. And then the route targets, the extended community, BGP well-known extended community, which is basically used for EVI or WRF. So basically, if the MAC consists is attached to that RT, it's used for bridge, as well as if it's under the WRF, it's used for routed. Then the tunnel attributes. For this case, we are looking at VXLAN, but this tunnel type can be anything like NVGRE or MPLS over GRE. Any of the options are supported. And tunnel attribute with MAC. So the MAC, this piece is very important because here we are specified as router MAC. But if it is router MAC, this particular field is important for integrated routing and bridging, IRB functionality. So if it is router MAC, it's routed. Whereas if the MAC is pointing to host MAC, that means it's bridged. And more importantly, the MAC mobility sequence number. So this is very crucial in terms of VM mobility. So once a VM moves from one leaf to another remote leaf, so basically a new leaf will send out the same NLRI with a higher sequence number. Now this sequence number is integrated as part of the BGP best path computation. So it's included as, so basically that leaf will, in terms of the best path computation, so BGP will always pick that sequence number with the highest sequence number as the best, okay, such that the traffic is no longer flowing to the older leaf, but it's converged to the newer leaf location. Prevents traffic happening. That is basically which is a problem with VXLAN flood and learn. And here just an example. Let's with the type 2 route, we are looking at an L2 overlay. So here you have VLAN 1 and VLAN 2. So basically VLAN 1 has MAC 1 on TOR 1 and MAC 3 on TOR 2, and VLAN 2 having basically MAC H2 on TOR 1 and MAC H4 on TOR 2. So here basically it's the TOR or the leaf is the same basically as far as it supports the L2 gateway functionality. Here basically we are seeing that this is still supporting the VXLAN tunnel endpoints. So the TOR 1 sends a type 2 route with MAC H1 pointing down to VNI 1, which is L2 VNI, and MAC H2 with VNI 2, which is L2 VNI or for VLAN 2. Similarly, TOR 2 sends out a BGP NLRI, type 2 NLRI with MAC H3 pointing to VNI 1 and MAC H4 pointing to VNI 2. So finally, this sets up a VXLAN tunnel between the TORs. And this is finally how the bridge traffic with VXLAN NCAPs of VNI 1 and VNI 2 are flowing over this VXLAN tunnel. So basically, but the only limitation is only a host on VLAN 1 can talk to hosts on VLAN 1 on the remote TOR. So you cannot talk from VLAN 1 to VLAN 2. It has to be on the same VLAN because it's an L2 extension, right? Okay, going down to L3 overlay. So this is basically for the routed traffic. So here the TOR 1 and TOR 2 both have the same VRF 1 with a VNI of 3, which is an L3 VNI, and it has 2 IP hosts on both TOR 1 as well as TOR 2. So it will send a type 2 route with an host IP with an L3 VNI. So both the hosts have the same L3 VNI. Similarly, TOR 2 sends back the same host, the host connected to TOR 2 with VNI 3. And finally, we have the VXLAN tunnel, and then we have routed traffic with VXLAN NCAPs with VNI 3. So basically, it's routed. Now going down to this type 5. So this route is specifically required in the data center. So it was not present in the earlier draft. This is currently earlier RFC, but this is currently in the latest draft. So with type 5, we have layer 2 extensions. So basically this is a pure L3 connectivity. It can be, and it is also having some intersection with type 2 route, but we cannot cover that area in a short span. So let's only concentrate on the layer 3 functionality piece. So here it has the RD, the Ethernet segment and the gateway IP address basically are zeros. It means that it's a pure L3 connectivity. Whereas if it has an overlay index, that means this route has some information in type 2 route. So it's dependent on type 2 route, and we can get back to that later. So for now, the IP address, here you're talking about connected interfaces. These are not host routes. These are basically addresses which are aggregates or connected routes, which can have multiple hosts lying behind that connected interface. So it will have a label 3 label, which is an L3 VNI, which basically points to the VRF, and a route target as similar as that what we have for type 2, and the same tunnel attributes which we talked about in the earlier type 2 route. Here's just an example. So basically we have leaf 1, leaf 3, leaf 4. They have the same L3 VNIs, and the moment a subnet or a connected host is connected to layer 3 VNI and it gets distributed into BGP. So BGP on leaf 1 will basically generate a type 5 route with the prefix pointing to 10.1.1.0/24 with an L3 VNI, the next stop pointing to the leaf 1, and the router MAC also pointing to that of leaf 1's MAC. And this route is sent out, advertised out to leaf 3 and leaf 4, because all the it looks like leaf 1, 3, and 4 are the ones which support the L3 gateway functionality. Now, the ones we talked till now is basically BGP EVPN in the data center. Much more the control plane and the traffic flows from east to west, much more looking within the data center. Whereas with data center interconnect, you're basically talking about control plane and traffic flowing out of the data center over an MPLS core towards a remote data center. So this is much more called as the north-south traffic. So in this case, you have a DCI called DC1, there's a WAN, and there's a remote DC. So here the options is, there's a border leaf, which exits out of the data center. It's connected to the data center interconnect. So the data center, here in this example, we are having the DC and the data center interconnect in the same AS, but it can lie in different ASs. There's no limitations. So what does the data center interconnect do? It internetworks. So basically it takes a EVPN VXLAN route and basically re-originates it as an MPLS L3 VPN route towards the WAN side. So here, that's how it provides the L3 DCI service. So it uses EVPN VXLAN on the data center, and towards the WAN, it's MPLS L3 VPN. And then it may go further down to another data center interconnect, which will be swapping it back into EVPN VXLAN. The second piece of services is L2 DCI. Here basically and the first one, L3 DCI, is basically used to extend the L3 connectivity from one data center to another data center. The second one is L2 DCI. So here you're trying to extend the L2 connectivity from one data center to the remote data center. So in this case, it is basically EVPN VXLAN running in the data center, whereas on the WAN side, you can have either EVPN MPLS, VPLS, or OTV, any of the flavors. So basically, it's just helping out in extending the layer 2 gateway functionality across. For this particular presentation, we can concentrate more on the layer 3 DCI service. So here is an example with the layer 3 DCI service. So we have an EVPN route type 5, because that is the one which will bring in the L3 gateway functionality. So we need to send this route out over the WAN towards the remote data center. So the data center interconnect basically takes the type 5 route and basically re-originates into an MPLS route. So basically, the MPLS route will have an RD prefix, MPLS label, RT, and next stops. So I think once we go to the next slide, it will give a much more clearer picture. Okay. Let's look at two hosts, host A and host E. So host A has an IP address of 111. So basically, firstly, it tries to see it wants to send packets out to host E, which is 555, which is in the remote data center. So firstly, with BGP EVPN running already in the data center, so we are able to figure out whether the host is present within that same data center or not. If it's not present in that data center, then that host route is sent out to border leaf. The border leaf is the exit out of the data center, which is connected to the data center interconnect. So the data center, the border leaf sends out a type 5 route 1110/24 with the MAC and the next stop pointing down to the border leaf. The border leaf is the exit out of the data center. And it will have an RT which basically points to the ASN number and the VNI ID and the NCAP, which is basically VXLAN. So the moment the DCR receives this route, it will re-originate it into an MPLS L3 VPN route. So either it uses the same RT or it will re-originate with a new stitched RT. So based on what will be imported on the remote WAN side. So here, basically, this should have both an RD and this EVPN NLRI will have both an RD and a prefix, as well as the MPLS NLRI will have an RD and a prefix because it's a multi-protocol BGP, but here just for simplicity purpose, we removed the route distinguisher. We just kept it as a prefix. Similarly, for any route learned from the client side, okay, like the prefix, which is replying back, which is 5550/24, it will have an MPLS label of 56001. So this route basically is re-originated into a type 5 EVPN route. So the DCI basically takes an MPLS L3 VPN route and re-originates it as a type 5 EVPN address family. So internetworking happening across the address families, which is BGP EVPN address family and the BGP MPLS L3 VPN address family. So here there are two options. The data center interconnect either sends the more specific, the specific route, which is 5550/24 towards the data center, or else it can send a default route. The default route is the best option because that will help to reduce the scale on the leaves. So the primary purpose is to reduce the scale. So basically here we are looking at one VRF. We may have thousands or close to 4K VRFs. So if it's 4K VRFs, you're looking at just 4K routes with the default route, right? Per VRF, one default route per VRF, rather than sending the entire more specific routes. So it will help to reduce the scale considerably within the data center. These are some of the nuances and limitations which you can go over once the slides are available to be downloaded. Okay, we're just coming down to the forwarding plane. So here, let's look at from traffic flowing from the WAN on the fabric. And here, the forwarding plane, we are looking from a DCI perspective. So how a DCI interprets a packet and forwards it. So the DCI receives an MPLS packet. So assuming it's a per VRF label attached to that packet, so he does a per VRF label lookup. He removes the per VRF label and attaches a VXLAN NCAP. So basically the L3 VNI and pushes it out on the VXLAN towards the fabric or towards the data center, which is a VXLAN packet. So this is for per VRF. If it is per prefix, he basically does a label lookup and removes the label and attaches a VXLAN NCAP, which is an L3 VNI label, and sends it out to the VXLAN packet. So this is the fabric to the WAN, the other side. So once we receive a VXLAN packet, we'll do a VNI lookup and then basically either do a VRF or per prefix label and send it out towards the MPLS core. Okay, these are some of the references. So you can either, most of them are RFCs and drafts. So if you need more detailed information or any other information, you can please send us an email. We have our email IDs listed out in the first slide. So we'll be happy to get back with more detailed information. Yeah, I think I'm done. So any questions? Thank you.